So we've been talking about indefinite integrals and anti-differentiation in the last section we looked at as a beginning of our introduction to integration. Now we're going to take a sidestep right now, and then we'll see how we can bring this back to that idea. So we're going to look at area. So just think about this problem here. Let's say we wanted to approximate the area of the region in the plane bounded by y equals negative x squared plus 5 over 0, 2, particularly above the x-axis. So this area down here is what we're trying to approximate. So this is not an easy area to calculate because we don't really know how to calculate a cutoff parabola by, say, geometry is normally how we calculate areas. So we are being asked to do to approximate the area. So the way that was originally looked at was a very simple way. What if we just approximated by using things that were familiar with their area? So like a rectangle. A rectangle is an easy thing to find an area. And if we just put a rectangle, say, here and here, and then did another rectangle that was maybe here and here, then if I looked at the areas of those two rectangles now, fill out the whole rectangle. If I looked at the area of those two rectangles, that would give me an approximation for what that area is. It's not certainly going to be exact, but it'd give me a ballpark estimate. So in fact, I could say that, well, this has a base of 1 here, and it has a height of 5 there, so this has a total area of 5 in here. And this one has a base of 1 here, and if this point is where it's intersected, that's the 1 point on this function, negative x squared plus 5, so that would actually be at the value 4. So this has a side of 4, so this would have an area of 4, and the whole area is approximately 9. Okay, so that's, I mean, obviously it's not the right answer because we've got this stuff up here in this blank region here that we're counting, which is not in the area, but it's a ballpark estimate. So how can we approach this? We're going to use rectangles. All right, very simple idea, but this is really what finding area under a curve is about, using rectangles. And the idea that maybe if we wanted a better approximation to this, we should use more rectangles. And so we'll use more and more and more and more and see how we can get to a better and better answer, and even the exact answer at some point. So let's try and get a little more specific about how we can get a structured approximation here. So think about a right endpoint approximation. The idea is that we have to decide how we're going to make these rectangles. So we have to decide how we're going to figure out what the height is and what the base is. So here's what we're going to do. Take an interval AB, subdivide that interval into n subintervals. So we're going to cut it into n subintervals. In that previous example, we cut it into 2 subintervals and hence got 2 rectangles. And they're going to be of equal length. So delta x is just b minus a over n, the total length of the interval divided by how many subintervals you're going to make. So let's say we take the previous one and instead we're going to subdivide it into 4 subintervals. Then each of the subintervals would have a width delta x, 2, that's b minus a over n, so we get 1/2. And as you can see here, that's what we'd be talking about. We have 1/2 here, so that's a 1/2. This is all a 1/2, this is a 1/2, and this is a 1/2. So that's because we've divided that 0 to 2 into 4 pieces. Now, the idea of using the right endpoint is that's how we're going to figure out how tall the rectangle is. So it's going to be based, the first rectangle is going to be based off of this right endpoint, giving us this value of the function, and that's why we're getting the rectangle as denoted here. So then we go to the next subinterval, the one from 1/2 to 1. Now we're going to use this endpoint of that interval, bringing us up here, and that's how we get the second rectangle. And on. Third endpoint, third point on the curve, that rectangle. Fourth endpoint, fourth point on the curve, and that rectangle right there. So if you look at it, look what we're actually saying. We've broken our interval into x0 to x4 here. So x0, x1, x2, x3, x4, because you need 5 points to make 4 different intervals, because you're taking the intervals in between. So if we're going to use the right endpoint, that means that when we're at 1/2, we're using f of the right endpoint x1, which is f of 1/2. Okay? And then it's the same thing, so f of 1 for the second interval. So let's look at how we could build this. So the area is approximately the area of these 4 rectangles. So the first rectangle has a height of f of x1 and a base of delta x. So that's what we're saying right here. The second one has a height of f of x2 and a base of delta x. And then f of x3 delta x, f of x4 delta x. These are the 4 rectangles area. Now notice, each one of them has a delta x in it. So that can be factored out. So then we just get f of x1 plus f of x2 plus f of x3 plus f of x4 inside. All right, so now we actually have values for some of these things. We have delta x was 1/2. x1, remember as we saw right here, was 1/2. And then x2 is 1, x3 is 3/2, and x4 is 2. So now we can get the function at those values. We know what the function is. It's 5 minus x squared. And so I have 1/2, f of 1/2. So put 1/2 in there. You get 5 minus 1/4, which is 20/4 minus 1/4. So you get 19/4. And then f of 1 would just be 4. So now f of 3/2, you're going to get 11/4, and f of 2, you're going to get 1. So if we go ahead and calculate that, that's going to give you 50/8, or 25/4. Oops. 25/4, or 6.25 square units. Okay, so that's an approximation. But look at this. This function is decreasing, right? This function is decreasing because it's going down like that. It's always decreasing. So all these rectangles are falling short of the function. So we're obviously underestimating. So for this function, since it's decreasing, the right endpoint approximation gives a lower sum for this choice of interval subdivision. So this is the lowest sum we would get, the lowest approximation we would get from using right endpoints. Well, we don't have to use a right endpoint. We can try another way.